Good afternoon, my name is Thomas, and today I will give a presentation for the COMP533 module. The topic I'll be speaking about today is matrices. First, I will start off by describing what a matrix is. In a maths context, a matrix or matrices is a table of expressions including not numbers or symbols arranged both in columns and rows to represent a mathematical object or property. A matrix is defined by the number of rows and columns it has. For example, a matrix with 2 rows and 2 columns would be called a 2 by 2 matrix. To further illustrate this point, I have provided more examples. For example, a row matrix only has 1 row and any number of columns. The column matrix only has 1 column and any number of rows. The square matrix has the exact same amount of rows and columns. The rectangular matrix is defined when the number of rows is not equal to the number of columns. The zero matrix is defined when all of the entities in the matrix are 0, and the identity matrix is when we have ones diagonally and any other entity in the matrix is a 0. Now, I will provide some brief historical background. So, the matrix was first used in a Chinese text during Han Dynasty, somewhere between 300 BC and 200 AD. One method that came out of this era is a Gaussian elimination method, which is used to turn the matrix into its row echelon form. And then, in the late 1600s, the theory of matrices was developed by a mathematician called Gottfried Leibniz. Furthermore, in the early 1800s, a mathematician called Carl Gauss advanced the matrix theory even further by adding more operations, for example, matrix multiplications and inverse, etc. And finally, in 1850, the term matrix was used for the first time. So, why are matrices useful? In the maths context, matrices are very useful as they provide a way to define linear and the differential equations, as well as representing linear application. In data science, they are also very useful as they give us the ability to store our data in a very organized way, which allows us to extract meaningful insights from a data. And finally, in physics, matrices are used to model a variety of complex phenomena, including simple rotations, to understand quantum mechanics. Here, I will provide a step-by-step example of an inverse of a matrix. So we start with our baseline here, and this is the matrix we wish to find the inverse of. Where to do so, we also need to put the identity matrix side by side and perform row operations. So to do so, we take row 1 away from row 3, row 2 from row 3, then we multiply row 3 by -1, then we take away row 3 from -2, and this gives us our inverse right here, which is our final product. So what real-world applications does matrices have? For example, in economics, they are used for maximization of assets, product manufacture, and managing supply networks. In robotics, they are especially useful as a robotic system can be represented in mathematical terms using rotational matrices. Also, another kind of matrix is the key matrix, and it can be used to encrypt messages, and the inverse of that matrix can be used to decrypt those messages. And finally, matrices are commonly used in graphic design and game design because they allow for the control of 2D and 3D graphics. This was my presentation about matrices. Thank you for listening.